Dias from USP, Parafermionic zero modes in strongly correlated fermionic lattices.
Okay, so thank you, Eduardo, for the introduction. I'd like to thank the organizers for the opportunity, for the invitation of giving a talk here. It's really nice to see all of you, not on a Zoom screen, but live. So I'm from the University of São Paulo, just a 40-minute subway ride from here. It's always a pleasure to be here at the ICTP. And this is the outline of my talk. Since there are several students here, I'll take the first few minutes to do a brief review on Majoranas and the other Kitaev model that is different from the one that was mentioned before. And then I'll talk about what are parafermions, or what they have to do with Majoranas, and whether we can detect parafermions with some scheme, very similar to some earlier work we did for Majoranas. And also the difference between Z4 and Z3 parafermions, and whether we can formulate a purely fermionic model, lattice model in 1D, where you have excitations, parafermionic edge excitations in these systems. And then I'll finish up with summary. So let's start with the Majoranas. We've heard from Eric yesterday, you just heard from Rodrigo about the famous Majoranas we all know and love. And they are a particular kind of parafermion in the language that I'm going to introduce now. They are so-called Z2 parafermions. So we all know what fermions are, right, in this community for sure. So let's define the Hilbert space for fermions. There's only two states, 0 and 1. And let's call this the empty glass and this the full glass, right? So, or you can say this is the antiparticle or the particle or the whole and the particle or whatever. And we all know the commutation relations for these, for the algebra for these operators. So we have a well-defined number operator, and we also have a well-defined parity operator that has two values, right? -1 or +1, the way it's defined here. If n equals 0, it's +1. If n equals 1, it's -1. So this is all no, right? So this is the Z2 parity, if you wish. Now, what are the Majoranas? So the Majoranas are a different representation. Like, we can define these self-Hermitian conjugation or self-Hermitian operators, which they are equal to their own Hermitian conjugate. And they obey this algebra, which is kind of similar to that, but with this very important distinction that if you square this operator, you get 1. You get the unity. And in fact, you can rewrite these fermionic operators in terms of these guys, these Majorana operators, right? As this, and you recover the same algebra that you had there. And you can also do the other way. You can write these Majorana operators in terms of purely fermionic ones. So this is, Majoranas 101. And that's what why we call, and Eric said yesterday, and Rodrigo too, that usually you call the Majorana half fermion. Essentially, if you do a combination like this, you get a state that obeys this algebra. And now this is a mixing of a full glass and an empty glass. So this might be the half-empty glass, if you wish. If you Hermitian conjugate it, the half-empty goes to half-full, the half-full goes to half-empty, you get the same thing, right? So this is the trick of the Majorana. It's just a similar, a different representation. And why do we talk so much about Majorana in these days? Well, over 20 years ago, Alexei Kitaev wrote this paper on this rather obscure journal, where he did a very, very interesting calculation, and he showed that if you write fermions in this Majorana basis, and you have a 1D system that has some P-wave-like pairing, superconducting pairing, meaning that you pair fermions on different sides or on neighboring sides of the lattice, plus some usual hopping and plus some local chemical potential. This model is sufficient to realize a system where you have a chain of Majorana fermions with the two in one of the regimes is that you have two of these Majoranas at the ends of the chain completely uncoupled from the rest, right? So this is the so-called topological phase of this P-wave, 1D P-wave superconducting wire, if you want. And now the idea here is to use those Majoranas for braiding and trying to construct some protocols for topological quantum computation. So that was 20 years ago, and the idea is rather simple, right? So if you have this chain of Majoranas, there's essentially two limiting cases. One, which is essentially maps into an insulator, is trivial. So you have, this chain of Majoranas, and they are connected pairwise. So the first Majorana is connecting to the second, and so on and so forth. And this, of course, as I showed you, you take two Majoranas, you can construct a fermion, right? So, or an electron. And this means that in this tight binding chain, you have isolated electrons each on its own side, and that's the definition of the insulator, right? Or a band insulator if you want. Now, there's another gapped phase, which is topological. In this case, the coupling between the Majoranas is between alternate Majoranas on different lattice sites. And that, if you have a finite chain, you eventually will end up with one free Majorana on one side and another free Majorana on the other side of the chain. And now you can think, well, these two here could constitute a fermion as well. It's highly non-localized, but you can, in principle, use these guys, these free Majoranas, to try to wrap them around and do what they call braiding, and then you might construct gates for topological or for quantum computation, which is kind of protected by the fact that these two modes are localized, at a very large distance, large in the sense, apart from each other. So the system, in a sense, has this topological protection built into it. So, okay, so this is the 2001 paper, and then a lot happened since then, and there are proposals for realizing these systems in condensed matter platforms, such as nanowires, semiconductor nanowires with induced superconductivity, magnetic chains on superconducting surfaces, and more recently, vortices on, say, iron-based superconductors. And all these, in a sense, a low-energy model for all these systems essentially map in some version of the original, the Kitaev model that I'm showing here is different than the spin Kitaev that you heard from Eric and Rodrigo. And this, well, it's been 20 years, right? So this is the first experiment that showed some signatures of these so-called Majoranas at the end of the wires. But then the community got into a kind of a, I don't know, in disarray when this very high-profile paper was retracted. So essentially, I'm not going to go into the details here, but essentially that cast doubt on all the previous results that were obtained for over 20 years, right? And now it's been very hard to get back on track. And a sign of the times is this paper, right? Which is, long-awaited, and there is, fire chat videos on YouTube with people like Shankar Dasarma and Chetan Nayak talking about how nice it would be to have a protocol that says, okay, we now have true-to-God Majorana on these devices. But then there's a paper with over 120 authors, right? So there's some sociological chain here that we're now getting large collaborations into condensed matter, right? And this, I mean, okay, and it's not the end of the story because now the discussion keeps going on not only on YouTube but on Twitter. You have Shankar Dasarma saying that, oh, now we have the Majoranas, and then you have the contrarians like Sergei Frolov and Vincent Murick doing a live read of the paper on YouTube, and and the controversy shift now from scientific papers to YouTube and Twitter. So maybe the next generation will essentially live in a world like that. And it's very interesting, but at the same time, it's very unsettling. All right, so this is I've been working on this for some time now. And at some point, I think it's nice to see if there's, physics, more basic physics related to that, but somewhere else, right? So that's when I started to look beyond Majoranas, and the one natural continuation were parafermions. So I started looking into that with a PhD student of mine, Rafael ago, and I had one simple question. First, what are these parafermions? And secondly, how can we get them in an electronic system, right? And that already led to 2 papers, and we're still far away from a definite answer to those questions. So let's give you a hint of what we're doing here. And perhaps that's precisely the path that Kitaev took over 20 years ago. So he reverse engineering the model. Now, and I'm not going to go into that, but this chain of Majoranas was already known, and these properties, essentially the topological properties, were essentially already known at the time when he wrote the paper. And now if you start with a chain of Majoranas and you reverse engineer it, and you write the Majorana operators in terms of fermions, you will get a fermionic model, right? So if you know that, okay, I want a chain of Majoranas with the 2 at the end uncoupled, let me reverse engineering and say, what kind of fermionic system will give me that? And you get precisely the 1D P-wave superconductor, right? So that's the essential path that we're going to take here, now using parafermions. So what are parafermions? And usually when it comes to this part of the talk, people start talking about clock models and spin chains. And I'm going to do a little bit different, because that's the way that works for me, and to already write this in terms of a Hilbert space of a very few states, and try to generalize that to get the algebra that we want. So I'm going to first define what Kobayashi and Ortiz define as Z4 Fock parafermion. So it's an operator D that you apply to the vacuum, and you keep creating a 4-site Hilbert space, right? And these operators have these properties that, well, if M is E1 or 2 and 3, and you have D dagger M dm plus D4 minus M, D dagger 4 minus M, you get 1. And you have a well-defined Fock parafermion number. And my battery is done, so I'm going to switch to this one. And then, sorry. If you now also have a well-defined parity operator, but now this is Z4, meaning that it has, instead of plus 1 and minus 1, you have 4 numbers, plus 1, plus I, minus 1, minus I. And you can rotate around these. Each of these operators are essentially each of one of these states are eigen states of these operators. And now you can construct the parafermions this way. Your parafermion operators will obey this algebra that if you dagger them, it's equal to the same operator to the 3rd power. And you have 2 of them. And if you put them to the 4th power, you get 1. So this is already a generalization of your Majorana. Yes? Yes. You can, yeah, like these ones, you can write them precisely in terms of the operators that appears in those clock models. Yes. So not these ones, but these ones, yes. So, and they already have, for the Z4 clock model, in this case, right? And they already have anionic statistics right off the bat, right? So if you switch them, you get this I instead of minus 1. Now, the question is, whether you can, one thing is that I chose Z4 for a reason, because there's a hidden Majorana in there. So if you square either one of these, they will behave like Majoranas. So within this algebra here, there's the Majorana, a Majorana algebra hidden there, and we're going to see that appear as one of the phases that we get in our models. So the next question is, okay, I understand what parafermions are, and can we get a Kitaev-like chain of parafermions? So we just write the chain, right? So we have these operators here, and we write a chain of these operators. There's a phase here to, not going to go into details, but this is actually to get the prefactors correct and whatnot. But here, already I have a chain where j equals 0 is not, well, j equals 1 is connected to chi 2 and so on. So chi 1 is free, and psi L is also free. They are not present in these couplings here. So already start from a chain with two parafermionic modes free at the end. And the idea here is to reverse engineer that and get a fermionic model and see if we can solve that, right? So if we do that, and there's a representation for those four states in terms of fermionic states, the up and down times I, down times minus I, and the vacuum. These will essentially form the same algebra that I had, and if I define these D's in terms of the fermionic operator, notice here that I have 1 and 3, right? So parity here will be conserved in that sense, and also these Z4 cycling will also be conserved. And now I'll reverse engineering and write the chi and phi in terms of D's, but the D's are written in C's, and I take many pages of calculation and get an effective model in terms of my fermionic operators. And what do you get out of this? Well, you get some very complicated Hamiltonian, which has, let's bear with me here, you have all these terms. First, you have this P-wave-like superconducting term, but now for spinful fermions. But you also have interacting terms, and these can be nasty. I mean, you have a two-body-like interaction term with some spin flip at some point. You have some two-body-like P-wave pairing term as well. And you have some sort of spin orbit kind of term that is three-body in nature. And you also have P-wave pairing, which is three-body in nature. So you have, say, a number operator with opposite spin, and you have a pairing operator here. So it's a complicated fermionic model, but in the limit of T equals delta equals W, you map exactly in the parafermionic model I showed you. So what do you get here? Let's look at what we get if the interacting terms and delta equals 0, you have the trivial metal. That's one of the phases. If you have no interactions, right, none of these terms here, you only have the P-wave pairing, you essentially have two copies of the original Kitaev chain superimposed on each other, one for each spin. So it's like 2 times 2 Majorana modes, two chains of equal, so it's not very interesting too. And now when you have the whole thing, delta equals W equals T, now you get the gap system with parafermionic zero modes at the end. And that's the phases we'd like to see in a calculation, in a DMRG calculation, say, for this model, looking for, say, degeneracies in the ground state. And in fact, we did that, and we get precisely that. We get a phase diagram like this, just looking at the gap and the degeneracy of the ground state. Is not so easy because you have those three-body terms that can complicate your life. But at the end of the day, we get these three phases: a trivial phase, a metallic one, this 2 times Z2 or 2 Majoranas, and the Z4 phase here, which is topological, and you can go from each of them. All right. But now, the question that we asked in this work is, how can we detect this using something else? And the idea now is to add a quantum dot to this chain, couple it to the end of the chain, and look at the local properties of the quantum dot and see if we can get the same phase diagram, right? So that's essentially what we did. We have another site here that is just a regular Hilbert site with energies and 1 U, and in principle you can change these energy levels here. And now we want to calculate the local density of states of this guy and see if that gives me any signatures of which phase you are in the phase diagram. And if you do that, you get something that essentially maps the same phase diagram, but just by looking at the local density of states at the dot. Now you have the Z4 phase, which is this blue line here. You have the trivial phase, where essentially you see nothing in the dot at 0 energy, of course, because there's a gap there. And you also have a signature for the 2 times Z2 Majorana phase. And notice that in both of these topological phases, you have some signature of this 0 mode that was in the chain, but kinds of leaks into the dot, right? So it appears in the local density of states in the dot just via some regular coupling. And this was already known from the Majorana case. We did some work on that. And in fact, it happens here also in the parafermion, for the parafermion chain. And so you could, in principle, differentiate these three phases just by looking at the density of states at the dot. But if you also look at the density of states at the first side of the chain, you also see a very large difference depending on where you are in this phase or in this other phase. So if you are in the Z4 phase, you still have some residual signature in the local density of states there. But if you are in the Majorana phase, the 2 times 2 Majorana phase, you see nothing. So these are spectral signatures, yes?
Maybe I missed your explanation, but how do you differentiate between the phases with row, for example, the blue and the red?
So just by the height of the density of states at the dot. So this is essentially twice the height in this phase as compared to this one. And this one is essentially 0.
Yeah, but I mean, it's just a number, right?
Yeah, OK. I'll get to that. So there's another way to differentiate that coming from the charge. And I'll get to that. Yeah, but that's a good point. Right? Experimentally, it's really hard to differentiate these two. All right. But here, in the first site of the chain is very clear. All right. So if you change now, another way is that if you change the gate voltage in the dot, the behavior of the density of states in the two cases is different as well. So this is the Z4. It has, this is essentially, you have to subtract the background, but while the density of states in the 2 times Z2 phase is essentially just a smooth curve. In this case, you have more of a V-shaped behavior related to some background, if you wish. So this is another, it's a very small signal, okay, but it's still there. And most importantly, you see a jump in the charge of the dot once you cross, say, the particle hole symmetric point in the Z4 phase that is not there in the 2 times Z2. It's just a smooth, if you look at the charge, you see this jump here, which then you could detect, say, with a quantum point contact experiment or something like that. So not only the local density of states, but also the charge. Okay. So this is also, yeah, so, and if you differentiate the charge, you even get another signal that should be different for the two phases, right? Okay. So this is for Z4, and now we ask the same questions now for Z3 parafermions, which are very different in nature, and I'll tell you essentially because we don't have this hidden Majorana in it. So what are then Z3 parafermions? We just play the same game, right? We have these Z3 Fock parafermions that I come up with an operator that creates a cyclic three-state Hilbert space. And I define this algebra, this number operator, and this Z3 parity now is 1 e to the 2 pi I over 3, e to the 4 pi over 3, and back to 1. So it's cyclic like that. And you have to have these states as eigenstates of this parity, this Z3 parity operator as well. And now you define your Z3 parafermion operators, which obey these properties. If you dagger them, is equal to square them. And if you take them to the cubic power, you get 1. Notice now that there's no hidden Majoranas. So there's no combination of these operators where if you dagger them, you get the same thing as compared to the Z4. Meaning that here, there is no phase where you have just double Majorana phases, like in the other one. So this would be more interesting. And there's another reason why these could be interesting, is that you cannot do universal quantum computation with Majoranas alone, or Z4 parafermions alone. These are usually referred to as Eisenanions, and I'm not going to go into the details. But in principle, with Z3 parafermions, you could come on a phase of, depending on how you couple these Z3 parafermions, into a phase where the excitations are Fibonaccianians. And that could be useful for some universal quantum computation. So there's some interest in the Z3 parafermions because of that. Since then, you could have an all topological quantum computer universal and no need to rely on non-topological elements to do quantum computation. So, but that's just the background, and the question is how do we get these Z3 parafermions out of a fermionic model? So we did the same, and how can you in principle realize these parafermions in a real experiment? We know that if you can realize Majoranas if you have an interface of two quantum Hall chiral modes, just regular quantum Hall nu equals 1, for instance, with opposite spins on an interface with some superconducting pairing between them, and that's being known. This is the so-called Fugain-like model. But if you replace these chiral quantum Hall modes by fractional quantum Hall modes, like nu equals 1/3, you now will get Z3 parafermions instead of Majoranas. So that's one of the routes that has been thought in order to realize these Z3 Majoranas. So you need to have, it's a very hard experiment to do. You need a fractional quantum Hall chiral state, and you need to somehow put them in two sides of a superconducting layer and induce superconductivity and coupling, and then you might get some parafermionic mode at some point. So we're still very, very far from that, but we can still explore what you get if you can get something like that out of regular fermions. So just to finalize the message here is that we can do the same trick for reverse engineering the model for the Kitaev, and then you get some ugly things. You get ugly to the point that you have a very strongly interacting fermionic model that violates parity. And this usually is not a good thing if you want to actually do electrons, use electrons, because then you get terms that not only violate parity, but they have two-body interactions with spin flip, plus some weird trailing terms here that come from how the parafermionic algebra works when you put them in a lattice. So this is a problem. So if you do just the reverse engineering I told you about, that's what you get. But then we try to, we have these string factors that I mentioned, that these are all problems. But then Rafael figured out a way to get a similar Hamiltonian that is parity conserving and doesn't have strings attached to it. And the whole task of the paper is to prove that this model maps into the topological phase of the other one. And I'm not going to go into the details, much of the details due to the time constraint here. But this is still a very hard problem. The price you have to pay is now you have three-body interactions all over the place, but it still preserves parity and is a fermionic model in a lattice. And we heard about entanglement entropy here. And this just to tell you that entanglement entropy is one of the signatures of the topological phase transition in this system. We have a peak here showing that as you go, say, increase the interactions, you get a transition from a ground state that has no degeneracy to a triple degenerate ground state, which is the topological phase. And we showed that these two models, if you interpolate them, adiabatically, you go from one ground state to the other without closing the gap. So that's a good sign that the transition is topological. And several other signatures from, say, the entanglement spectrum in the DMRG. The ground state degeneracy is always 3. So it's always in the topological phase where we want them to be. Now we can calculate the spectral density at the end of the chain. For the exact chain of uncoupled parafermions, you get the green dots. And these are the DMRG calculations for H1, which is actually harder to calculate with the DMRG because of the three-body terms. And you get something very close at the edges. So you have these edge states also showing up in the calculations. All right, so let me skip that. And if you want to learn about local operators like, say, a Zeeman term apply both in plane and at the Z, you get this symmetry where you have the gap closing at these angles, which nicely reflect the Z3 symmetry of the system. Local disorder, we did a little bit to put some local terms and see if this phase is resilient and robust against small disorder, and that's one of the things the referee asked us to do. And yeah, so the answer is that we can get Z3 parafermionic modes out of prior fermionic models, while this is not obvious that we could get because of the parity and the fact that you don't have the mapping to Majoranas. That's one of the nice results of this paper. And on the other one, we could use a quantum dot to map the actual phase diagram of the system. So before finishing, let me just mention that all this was the PhD work by Rafael. Some of the other members of the group are here. So João and Lauro are presenting posters today. And Bruna presented the poster yesterday. And that's it. Thank you very much for your attention.
Questions?
So very nice talk.
Thank you.
So this is a very basic quantum mechanics question, possibly very naive. But how does that translate as parafermions in which you can put more than one fermion upon the vacant? How does that translate in terms of the symmetrization of the wave function of the many-body wave function? I mean?
Okay, so it's anionic, right? Even in the Z4, if you switch now our generalized fermions would be these these Fock parafermions, so these Ds. Now, like in this state, I have 2 of them. And if I switch them around, I don't get a -1. I get some other phase. In the Z4, in the Z4, you get the phase is pi over 2. Here, let's see. So the wave function that you get is definitely not the textbook fermionic wave function that you get, especially if you have many of them. So like here, yeah, you can sort of see it already here, right? So the exchange, if you want, the exchange property is different than what you get for regular fermions right off there. So.
Yeah, but on the other hand, in terms of the C fermions, the parafermions are sort of non-local operators, right? So,
well,
so this question of having 2 on the same site is hard to see in the wave function, I would think. Because what you can put 2 is D, but D is that strange thing over there. So
yeah, you have to construct something like that, right? So D you can write in terms of the fermions.
And that we know cannot have double occupancy. But D, perhaps. Okay.
I mean, this state, I up down, has a Fock parafermion number of 2.
Right.
So, yeah.
Okay.
Yes, thanks for the talk. But somewhere you use this term, universal computer. What is that?
Okay. All right. So Bruna, where's Bruna? She's an expert on this, and I'm not such an expert. But let me tell you that when you have, so yeah, let's go back to Majoranas. I might have a slide here on braiding. So the name of the game is braiding. Let me see. Yeah, something like that. So if you have 2 fermions and you exchange them, you get a -1, right? So if you have this blue thing and put it here, and this other one, put it there, the overall phase that you get is -1. Now, if you have individual Majoranas, you don't always get that. You get some combination that might not be 1, and you can use that to do, essentially, if you now go into the language of qubits, if you want, you can use these braiding operators to map that into qubit operation, like matrix, right? But the thing is that because of the properties of the Majoranas, it's not every operation that you can do with qubits that you can realize here with these Majoranas. Some of them you can't, precisely because you have these rules, right? These braiding rules of gamma 2, gamma 3 equals minus gamma 3, gamma 2. So now if you have not Majoranas but Z4, your phase, instead of being I to the pi over 2, right? Your rotation in Hilbert space, you can do, instead of 90 degrees, you can do in 45 degrees intervals, but it's still not enough to get a continuous rotation in a qubit space, for instance. So you need, at some point, you can realize some of the gates, but not all of them. I think the Hadamard you cannot, right? Or yeah. Okay. So if you want to build a computer out of Majoranas, you need some element that's not going to be topological. You need to do this rotation using some other scheme. So your computer will have a part that is non-topological, and there you can get dephasing very quickly. So with the Fibonacci anyons, I'm not an expert, but what the paper says is that you can. Right? You can construct a universal set of qubits, of qubit operations that will realize a universal quantum computer.
Okay. Thanks.
Other questions?
Hi, nice talk.
Thank you.
Let's continue this conversation about quantum fault-tolerant computation. I was wondering that if you want to use Majorana fermions to make this computation, you have to attach one vortices, right? I mean, Majorana zero modes bound into a vortex. You can exchange braid them and create a scheme of quantum computation. I was wondering if parafermions have the same scheme, like if you attach a vortex to parafermions, what doesn't happen?
Yeah, so exactly, that's braiding with parafermions. That's your question, yeah. You can do that. Let me give you an idea of how that might work. So the Majoranas, they have this simple exchange rule, right? You still get a -1 when exchange two of them. And now you can use that, to say if you have 4 Majoranas, you start getting all these rules here. The Z4, instead of the -1, you get an I. So a phase of pi over 2 instead of pi. And then you can do the same trick, and then you have to work out the algebra to see what you get when you braid parafermions this way, and try to now map this into a qubit kind of form where the result of your operation of braiding would give you what you expect for your gate to do in qubits. Yes. Yes.
Basically, it's like Majorana zero modes with a different phase.
Exactly. So yeah, you at the end you have to map some 2-particle state into something else that's not going to be one. It's going to be some combination, the precise combination that you want your qubit gate to do. And now take some imagination to see what kind of braiding you have to do. Sometimes it's more than one, usually.
What questions?
So I was just wondering, did you ever try to write these Fock parafermions in terms of higher spin operators, spins larger than 1/2?
We didn't try that because we want to have electrons at the end of the day.
Okay.
But I think in the paper by Cabaneta and Ortiz, they do that. They relate that to, say, the algebra that you get in spin clock models.
Okay.
So, because, in clock models with the correct spin, the algebra comes out nicely. So it's not this complication that we get. We're essentially getting this complication on purpose because we want electrons at the end of the day.
Okay.
But yeah, if you allow yourself to work with other objects with higher spin, I think your life will be much easier.
Yeah, okay, okay.
More questions? Okay, so if not, let's thank Luis again.
Thank you.